Welcome to the Barriers to Hyper-Retiming online training. My name is Marlon Price and I will be the presenter for this training. Hyper-retiming, or the use of hyper-registers, is crucial to your designs reaching the highest possible speeds in FPGAs that are built with the Intel Hyperflex architecture, currently the Intel Agilex and Intel Stratix 10 families. So if you're trying to maximize your design performance, you want to make sure that your design is written in a way allowing as much retiming as possible. Since the Hyper-Retimer, or the retime stage in the Quartus software, is required to keep the retime design functionality equivalent to the original, the Hyper-Retimer has strict rules to follow as to whether a register can or cannot be moved. So it is important to know what the rules preventing retiming are so you can limit the number of these conditions in your design as much as possible. By the end of this training, you will be able to identify common circuit structures that limit hyper-retiming. You will also learn techniques you can use to optimize these structures, including code changes and Quartus software constraints. During the training, we will first talk about retiming, how it is performed, and the impact of design structures called retiming dependency nodes. Then we will discuss restrictions that serve as barriers to retiming and in many cases how to remove them. Finally, we will look at how you can use fast-forward compile to analyze the effects of hyper-retiming on your design. So first, let's start with a look at retiming and retiming dependency nodes. Looking at most FPGA designs today, we see literally thousands of converging and diverging paths. These are paths where multiple branches reduce or merge into a single path or a few paths, or where a single or few paths split into multiple branches. In order to ensure correct functionality is maintained, the Hyper-Retimer must follow strict rules when it comes to retiming through these converging and diverging points. The rules that control hyper-retiming are dependent on your design topology. In order to retime a register forwards through a structure and maintain correct functionality, first, all inputs to that structure must be able to provide a register to move through the target register. So using the example on this slide, if the Hyper-Retimer wants to retime the red register forwards, then the other two inputs to this structure, the yellow registers, must move to be able to be retimed along with it. Second, all outputs to that structure must accept a register. So in our example again, both blue dots must be free and able to accept a register that is retiming forwards. The same is true if retiming backwards. All outputs to the structure must provide a register, and all inputs to the structure must accept a register. The combinational structure through which the registers retime is referred to as a retiming dependency node. This retiming dependency node forms the basis for understanding how retiming works and what happens when retiming cannot be performed. The retiming dependency node has the effect of binding input source registers and output sync registers together, meaning that any retiming action to one will impact all the others with respect to that node. A simple way to define the retiming dependency node is to say this. If you want to retime a register from one location to another location, then the entire structure between those 2 points is a retiming dependency node, whatever that structure is. Thus, a timing dependency node structure can be any logic structure like the diagram in this slide or the last slide, or it can be just a simple connection point. We can draw a simple cloud around it just to highlight the relationship between all the points on the cloud and the fact that the combinational logic structure within is immaterial. Be aware that this dependency can many times cause unintended retiming consequences due to non-critical side inputs on retiming dependency nodes. These side inputs can be input signals like control signals to registers or select lines to muxes. As additional inputs to the retiming dependency nodes, they can inadvertently prevent other registers in the data path, for example, from being able to move. This example highlights the unintended consequence of non-critical side inputs. At the top, you have 3 AND gates in series. Because of the long delay going from the input of AND gate A to the output of AND gate C, the Hyper-Retimer wants to retime some register forward. Since we want to move registers from the input of AND gate A to the output of AND gate C, then the entire structure becomes a retiming dependency node. This means that all inputs to the node have to provide registers in order for any registers to retime forwards. By design, AND gate A has plenty of registers lined up to retime forwards. The same goes for AND gate B. Unfortunately, AND gate C has one input and a single register. Once that register retimes forwards along with the first registers into AND gates A and B, then there are no more registers to retime. Thus, forwards retiming is now blocked through the entire structure after the first retiming move is completed. With all of the registers and all of the converging and diverging paths in an FPGA design, retiming becomes very complicated very quickly. A simple register move can translate to the movement of many other corresponding registers. In our example on the right here, registers 1 and 2 are too close. So we want to retime register 1 backwards and register 2 forwards. If we retime register number 1 backwards, because of the converging point, it needs to be duplicated into 3 register locations along that path. So all 3 new locations must be able to accept a register. If we retime register number 2 forwards, because of the diverging path, it must be duplicated into 5 register locations, and all 5 new locations must be able to accept a new register. Since registers number 3 and number 4 are also connected to the converging point fed by register number 2, they must also retime forwards along with register number 2 as shown in the lower diagram. If registers number 3 and number 4 fed out to other points, then those paths would have to retime as well. And if any of these additional paths could not provide a register, then register number 2 would not be able to move forwards. This here is just to highlight how complex retiming dependencies can be and the challenge the Hyper-Retimer may face when trying to do what seems to be the simplest of retiming moves. Because of the interaction of registers around retiming dependency nodes, if a register is blocked from moving, then neither its source or sink retiming dependency nodes can be retimed over. This can occur if the register itself is blocked from moving or if a corresponding register, another input or output to the same retiming dependency node, cannot move. In the example on this slide, the register shown in red cannot move due to a retiming restriction. Thus, input registers to the retiming dependency node on the left cannot retime forwards, and output registers to the retiming dependency node on the right cannot retime backwards. Thus, retiming is completely blocked at this point in the design. The same behavior occurs if the red register did not have a retiming restriction, but the gray register below it was empty. Since there is not a register there to move along with the red register, then the red register is still blocked from retiming forwards or backwards, and again, the retiming dependency nodes on either side are blocked as well. And remember, like we saw in the last slide, one blocked register can have a cascading effect, preventing many other seemingly unrelated registers from being retimed. Now that we understand retiming, retiming dependency nodes, and the effects of retiming dependencies a bit better, let's look at some specific factors that prevent retiming. Endpoints are points along FPGA paths at which retiming cannot be performed. They are the cause of limitations in your design's maximum performance. In the example here, we have a path with an endpoint shown on each side. Since the endpoint registers cannot move, then the performance of the paths between them is affected. The only thing the Hyper-Retimer can do is spread the registers out in between the endpoints as much as possible to average the delay between them. But the performance as determined by the average delay cannot be made any faster. To fix limitations induced by endpoints, you must either employ a hyper-retiming technique to remove the restrictions preventing the endpoints from being retimed, or a hyper-pipelining technique, which includes adding more registers to reduce the average delay. Some common design situations that prevent retiming are listed on this slide. They include asynchronous clears and logic tagged with the user-preserved synthesis attribute. We will discuss these restrictions in more detail in the upcoming slides. Probably the single most common retiming restriction is the use of asynchronous clears on registers. Why are asynchronous clears such a big problem? The reason is because hyper-registers are simple D flip-flops, and as such, they do not have asynchronous clear ports. ALM registers in the logic array do, but hyper-registers do not. They may be synchronously cleared, but we'll talk about how that is done later. So the recommendation for designs targeting the Hyperflex architecture is to remove or avoid using asynchronous clears as much as possible, except for the minimum needed to achieve a known reset condition and to protect outputs driving other devices or logic. If your design does not make use of asynchronous clears, then you're all set. If it does, then in relation to all of the potential Hyperflex modifications, this is considered to be a minimal design effort fix. Many FPGA designers have already started to move away from using asynchronous clears. With the clock speeds of today's larger FPGAs, it has become increasingly more difficult to meet recovery times when using the global clock trees to distribute asynchronous clears than in the past. Use caution though. Modifying the resets to your design changes how your design initializes upon power-up or after a reset is issued. So you must make sure you understand the FPGA's reset behavior, and you should revalidate your design again with the modified reset strategy. This slide provides an example of how resets can be removed from a design. In the diagram on the left, every register is asynchronously cleared, so they all must be implemented in ALMs with no hyper-retiming. One alternative circuit to asynchronous clearing all registers is shown on this slide. Here we have replaced the first register's asynchronous reset with synchronous reset, and we removed the asynchronous clears on all registers except for the last. Instead of resetting all the data pipeline registers immediately, we allow the circuit to naturally reset, meaning we assert the input reset long enough so that the reset from the first register propagates through the rest of the data register pipeline. We guarantee this by implementing a shift register chain in the reset line. This could also be done by connecting a counter in the reset path. This reset on the final register remains to protect the outputs, meaning it ensures the downstream logic driven by this register does not detect any difference in behavior. Of course, the reset on the last register could also be removed if not required by the design. How do you ensure your design naturally resets? Well, you must verify that the modified design can reach the same steady-state reset condition as the original circuit. The diagrams on this slide now include an example pseudo simulation. On the left, of course, for as long as the reset is asserted, the register outputs go to 0 and stay at 0. With the modified circuit on the right, when the reset is asserted, the shift register chain holds the asserted reset applied to the first data register, allowing its output to propagate all the way through the design. So you can see with enough clock cycles, the steady-state reset condition of the two circuits is the same. If the modified circuit was unable to achieve the same steady-state reset condition, then the circuit does not naturally reset. If the modified circuit does not naturally reset, then other reset solutions can be explored. Another way of removing clears is to use a valid signal pipeline. With a valid signal, a data word is qualified by means of a 1 on the valid line. Invalid data, when the valid signal is 0, is simply ignored by the downstream logic, shown in this diagram simply using an AND gate. You just need to match the number of registers in the valid pipeline with the number of registers in the data pipeline. Now, the data path does not have to naturally reset as it is protected with the valid signal. And the valid signal itself does not have any logic in its path, so in effect it always naturally resets. Let's take some time to talk about other register control signals, namely synchronous clears and clock enables. In order to remove asynchronous clears from a design, a designer may wish to replace them with synchronous clears. This may seem simpler than removing asynchronous clears and trying to implement naturally resetting logic. And while this is a possible solution for the Hyperflex architecture, you must be aware that synchronous resets are not free. Hyper-registers are simple D flip-flops. So while they do not have asynchronous clear controls on them, they also do not have synchronous clear controls either. But a hyper-register can borrow the synchronous clear from the ALM register upstream. In order to retime, the ALM register is disabled and bypassed so that its data input can flow to the hyper-register downstream. This same bypass path also allows all synchronous inputs to the ALM register, including the synchronous clear signal, to bypass the ALM register and be used by the hyper-register downstream. The result is the synchronous clear functionality on a hyper-register. The challenge here is that to do this, an ALM register location is still required, even though the ALM register itself is not used. This may make it difficult to retime, as this adds another input to the retiming dependency node, which can hinder retiming, as this means an extra synchronous clear input must be able to provide or accept a register in order to support other retiming moves. In addition to hyper-registers on routing channels, you will also find hyper-registers on all ALM inputs. This includes the data inputs to the lookup table, the data input to the ALM register, and the synchronous clear input to the ALM register. This synchronous clear hyper-register provides a location for retiming when the compiler wants to retime a register backwards. Again, the synchronous clear is an input to the retiming dependency node, so if we want to retime the data path backwards, the synchronous clear input must also accept a register. As we've just seen, simple retiming moves can be easily handled by the architecture. The challenge appears when S-clear signals have a high fan-out. A high fan-out signal creates a large retiming dependency node as all of the paths are tied together. So retiming one path might mean having to retime many corresponding paths sharing the same control signal. And if a register on any one of those paths cannot retime, it can effectively block the target path from retiming. High fan-out signals also cause retiming imbalances as well. If a signal has a fan-out of 5,000, some of those downstream registers will be placed close, but others will have to be placed further away. If, for retiming, we want to retime one of the longer paths, because they are one large retiming dependency node, the shorter paths must be retimed in the same way. But the shorter path may not have enough register locations available on it to support the number of registers needed for the long path. So the shorter path blocks the longer path from retiming. Finally, global routes do not have hyper-registers. So if a high fan-out S-clear is distributed using clock trees, a common practice by FPGA designers, this can challenge the retiming even further. If retiming the data path means pushing registers into the S-clear path, but the S-clear path uses a global which does not have registers, then the data path can again become blocked. The takeaway here is that synchronous clears, though possible, can make retiming more difficult. For high-speed designs, we recommend avoiding synchronous clears whenever possible, particularly when writing new code. Even though the device architecture supports retiming registers with synchronous clears, designs can easily run into retiming roadblocks depending on where those clears appear and how they're used. However, this may be simply unavoidable, particularly for functions like control logic and loops. If porting existing designs to the FPGA with the Intel Hyperflex architecture, then you can try to remove as many synchronous clears as you can while still maintaining proper functionality. For example, while the controlling state machine should be able to be reset, is a reset required for your data path? If you have logic that must be reset, like state machines or feedback loops, such that complete removal of the resets is not an option, then one possible retiming friendly solution is to add pipeline stages to the reset path along with the data path. This prevents the synchronous reset path from blocking data path forward retiming, which would happen if the reset path was unable to provide registers. Another way to make your synchronous clear more retiming friendly is to minimize its fanout. High fanout can cause timing issues in traditional FPGA fabrics, but as we discussed before, high fanout synchronous clears, even using global routes, is a quick way to run into retiming issues. So in this method, we reduce the synchronous clear fanout by localizing the signal. One way is to create a synchronous clear tree, duplicating the synchronous clear for different clock domains or for different hierarchies. This way, the local synchronous clear can be placed on a smaller, faster clocking resource with smaller skew. Another variation is to distribute the asynchronous clear globally and then synchronize it into local blocks. What works best depends on your design requirements. Some designs may require all logic to be released simultaneously from reset. Thus, the synchronous clear tree must be balanced, which can be challenging to implement and maintain through design changes. Other designs can tolerate different blocks coming out of reset within cycles of each other, thus eliminating the need for truly balancing the synchronous clear tree and allowing for an easier solution. Again, the goal here is minimizing fanout. The Quartus Prime software provides two design constraints you can use to automatically duplicate registers to reduce fanout. These provide more flexibility and intelligence over prior automated fanout controls. These are direct register duplication and hierarchical register duplication. See the Quartus Prime Design Optimization User Guide for more details on using these assignments. In prior register duplication techniques, the register is duplicated in synthesis, so where the copies are with respect to their fanout must still be figured out. Direct register duplication leverages physical proximity of fanouts to create a specified number of localized copies. Just tag the high fanout register with the constraint and set it to the number of copies to make. As shown in the graphic on the right, you will get that number of registers and the copies will be located with respect to the logic that they are driving. Hierarchical register duplication lets you take a chain of registers and push them down into the hierarchy, making copies as needed. To use this constraint, tag the final register in the chain and indicate the number of registers to push. The software does the rest. Note the number of registers you specify will also be the number of hierarchical boundaries they descend. As D flip-flops, hyper-registers also do not have clock enables, but like synchronous clears, this doesn't completely prevent retiming. To implement the clock enable behavior, ALM registers have a feedback loop connecting the output of the register to the D input of the register through an input select mux. The mux can then select between driving the register input with a new value or the current value of the register. After hyper-retiming, unlike with the synchronous clear, the ALM register is not disabled. Instead, the ALM register is copied to be implemented downstream in the hyper-register. The original ALM register is still used to implement the enable functionality, but it is no longer in the main data path. That is handled by the hyper-register. So when the clock enable is asserted, the new value is passed to both the ALM and the hyper-register. When the clock enable is deasserted, then the last register value stored in the ALM register is then fed to the hyper register to emulate the clock enable functionality. Thus, local clock enables can be easily handled by the Hyper-Retimer, just like with synchronous clears, and can be done without user knowledge. Also like synchronous clears, broadcast or high fan-out clock enable signals can make retiming become very complicated very quickly. So logic duplication to reduce fan-out or adding additional pipeline registers along the enable path can aid in improving retiming results. If you are using clock enables to implement multi-cycle operations, then please refer to the follow-up online training on hyper-pipelining for recommendations on how to handle. Another retiming restriction is the use of synthesis attributes preserve, don't touch, or keep. All of these are used to prevent synthesis optimizations, mostly in the case of when we manually duplicate a register or logic and we want to prevent the synthesis tool from collapsing or optimizing the copies away. Since these attributes prevent all optimization, they prevent retiming as well. As an alternative to these attributes, we recommend using the attribute don't merge. This attribute specifically tells synthesis not to optimize away the specific duplicated logic, but has no effect on retiming. Another attribute, preserve register send only, may also be used as it is a watered down version of preserve, preventing certain synthesis optimizations, but in particular not affecting retiming. Some other design situations that prevent retiming are listed on this slide. They include 1. Synchronizer circuits. The first registers into a new clock domain will not be retimed. 2. Clock crossings. The last register at an exit to a clock domain and the first register in a new clock domain will not retime. 3. I/O boundaries. The first register fed by an input and the register directly feeding an output will not retime. 4. SDC timing exceptions. Registers targeted by false paths, multi-cycle, or max and min delay constraints will not retime, nor will any registers within the path of the constraint. 5. Select RAM and DSP block configurations. Multi-clock, mixed with, or initialized RAMs will not be retimed. Chained DSP blocks will not be retimed, though some of these restrictions may be eliminated in future software versions. And 6. Unpreserved initial conditions. If your RTL uses explicit register initialization, setting the register to 0 or 1 at power up, then this may prevent retiming if a retiming move cannot maintain that initialized value. These and other retiming restrictions, as well as potential solutions, are covered in much more detail in the Intel Stratix 10 FPGA High Performance Design Handbook. You can increase your design performance by eliminating the retiming restrictions, or since some of these restrictions cannot obviously be removed from your design, by using these points in your design as targets for adding extra pipeline stages to allow for more retiming there. This technique is covered in more detail in the follow-up training on hyper-pipelining. In this last section of the presentation, we will talk about how fast-forward compile can be used to help with hyper-retiming and performance improvement. As we have seen, the fewer the retiming restrictions, the more registers that can be retimed to boost performance. This is easy to do if you are writing new code, but if you are porting existing code, are you really expected to go through your design removing all possible retiming restrictions? While that is a potential solution, it can also be a lot of work. For this then, we will use fast-forward analysis. Recall from the fast-forward online training that fast-forward analysis virtually implements hyper-retiming, removing retiming restrictions as needed to improve performance. It then reports back exactly which retiming restrictions were removed, providing you with a list of modifications you can make in your design for better performance. It also shows an estimation of the clock speeds it achieved when the tool made those modifications. This can save you significant time over the number of design iterations it would take trying to figure this all out on your own. When fast-forward analysis is run, it returns a progressive list of optimizations in the form of fast-forward steps. Each step includes a list of recommendations or optimizations you can perform over the previous step to further optimize, with potential clock speeds provided for each. This it does up until your target clock speed is met. Since hyper-retiming is the first stage of optimizing for the Intel Hyperflex architecture, it will typically appear as fast-forward step number 1, unless hyper-retiming alone does not result in any significant gain. When that happens, hyper-pipelining will appear as fast-forward step number 1, and any necessary hyper-retiming optimizations will be contained with that step. So just select the hyper-retiming or hyper-pipelining step and follow the recommendations, removing the retiming restrictions indicated. Not every fast-forward recommendation can be implemented by the designer. So fast-forward analysis provides constraints that allow you to control the recommendations given, rejecting recommendations that you cannot or do not plan to implement. For example, say you have some legacy code that you are using in your design. You simply cannot modify the code to implement the fast-forward suggestions, so there is no use for fast-forward compile to return any recommendations targeting logic within this legacy code. So by using these fast-forward constraints, you can force the analysis to return a solution that you can actually implement, thus increasing the usefulness of your fast-forward run. To control your fast-forward analysis, there are two constraints that you can use. These allow you to reject a recommendation, or basically tell your fast-forward analysis to produce a solution that does not involve a particular recommendation. Both constraints can be applied globally, affecting the entire design, or locally, affecting a particular instance in the design. The bottom of this slide shows setting the options globally using the Quartus Prime Settings dialog box and Entity Base using the Quartus Prime Assignments Editor. Of course, they may also be entered directly into your QSF file. The first fast-forward control constraint is fast-forward compile asynchronous clears. This constraint can be applied to parts of the design in which you do not want asynchronous clears to be removed, forcing your fast-forward analysis to produce a solution more compatible with what you intend to implement. There are two settings to this constraint: Preserve and Auto. Auto is the default. In this setting, fast-forward compile will leave asynchronous clears intact unless they are determined to be limiting design performance, after which they will be removed. Preserve then forces fast-forward compile to leave the asynchronous clears in a particular block unmodified. By default, the preserve, don't touch, and keep synthesis attributes serve as barriers to retiming. During fast-forward analysis, these attributes may be removed if they are found to be a barrier to a higher performance. If select instances of these attributes cannot be removed so that showing you performance numbers without them is useless, you can control this fast-forward behavior using the fast-forward compile user preserve constraint. Like the asynchronous clear fast-forward constraint, this one can be applied globally or to a specific module. The options for settings are also Preserve and Auto. Auto is again the default, which leaves user preserves intact until they are determined to be limiting performance, after which they will be removed. Preserve is the one you use to leave all of the registers with preserved attributes untouched. So that concludes our look at barriers to hyper-retiming. In summary, retiming barriers or restrictions like asynchronous clears and user-preserved attributes can limit the effectiveness of hyper-retiming. So high-performance designs targeting the Intel Hyperflex architecture should limit their use or use techniques such as hyper-pipelining to minimize their impact. To aid in this process, utilize Fast Forward Compile to help with identification of these barriers to retiming. Intel FPGA provides many self-help resources when you need design assistance. For example, there are web pages called landing pages dedicated to specific FPGA technology like transceivers, DSP, OpenCL, and high-speed gigabit interfaces. There is a community forum, and there are hundreds of training courses available just like this one. One last thing, when you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you can think of ways in which it can be improved. This concludes this online training. Again, my name is Marlon Price. Thank you for your time.